Okay, I hope you're refreshed. We're going to keep the doors open so that it's less of a torture now. The second, the fourth part, and there is also a fifth part. The fourth part is registering and landmarking faces, because as Fernando also said, registration happens to be the most important part in face analysis. If you do your registration very, very well, it doesn't matter what classifier you're using, you will basically succeed if there is enough information in your features. So, for expression analysis especially, registration needs to preserve expression discriminative information, right? So, what does registration mean? I'm aligning two faces because I want to compare them. If I'm doing expression recognition, what I'm comparing is usually a neutral face and an expressive face. And the difference will tell me what kind of expression is going on there. All right. And the shape, when we say shape, what we usually mean is a set of landmarks. So X, Y, Z points or X, Y points. The mouth corners, typically the tip of the chin. Usually getting some landmarks along the boundary is useful because it helps you with the stretching. And models like active appearance models, they do this landmarking and registration jointly. Okay. Fernando mentioned a couple of times the Procrustes analysis. I'll go a little bit more into detail. I'll give you the details of a few fundamental registration tools, let's say. Not too much detail, but so that you can get a better feeling of what's going on here. Do you know who Procrustes was? Does it ring a bell? Yes. Okay. He was a bandit in the Ulysses. So when he was traveling, he comes across this bandit. And what he does, the bandit does, is he has a bed, a Procrustean bed, as it is called now. He forced the people on the bed, and if they were too tall, he chopped off the pieces. And if they were too short, he stretched them. So now, Procrustean bed is used for people who try to enforce their ideas on other people, by stretching them or by pushing them or chopping them. But here, what we mean by Procrustes analysis is that we have a shape, okay, and then you try to fit it to another shape. Typically, you're given a set of n shapes, let's say pi, represented as a set of landmark coordinates each. So if I have, let's say, a face image with 7 landmarks, the eye corners, the nose tip, and the mouth corners, that will be 7. I will have 14-dimensional vectors in 2D. And if I have, let's say, 100 faces, that will be 100 14-dimensional vectors. The first thing Procrustes analysis seeks to do is to find a consensus shape. Okay, what is the generic shape of these objects? And it does this by an affine transformation. So it assumes that shapes P and P prime are the same if they are related by a special similarity transform. So P prime is equals alpha times P times. So this is a rotation matrix, this is a scaling factor, and this is a translation. So this is overall an affine transformation. And the way you perform this analysis is you first find a mean shape, you center all your shapes, then you bring all your shapes to a common scale, and then you initialize the consensus shape randomly, let's say by taking one of the shapes as the initial shape. You rotate each shape to fit this consensus shape the best. You use a singular value decomposition to find the best rotation. And then you update your consensus shape as the average of these shapes. Well, you can update y each time you fit a shape to the consensus shape, or once at the end, like online and batch ways of doing. So if I give you, let's say, a bunch of landmarks, this will be the Procrustes analysis result on faces with, let's say, different expressions. So this will be the neutral faces aligned with Procrustes analysis, anger, disgust. And if you want to have a single consensus shape, what you do is basically you look at the points here, you take their mean, and that will be your representation. Now, in 3D, we have either rigid registration or non-rigid registration. Rigid registration means you have a 3D object, you don't disturb its shape, you just rotate or translate that shape and you fit it that way. In non-rigid registration, you can bend it. You can actually deform your object. And the most classical algorithm for rigid 3D registration is ICP. It's iterative closest point. It's a rigid method. You take a point cloud, and for every point on the point cloud, you find the closest match in, I'll give you the details in a minute. First, let me talk about the thin plate splines, which is the non-rigid version, a non-rigid registration. What this one uses is only the landmarks. So it actually transforms the landmarks to their homologues and then deforms the rest. Now, for doing ICP, you initialize your point set. Let's say you have 2 point sets that you want to align. Okay, P0 is your first iteration. You align, you set it to P, which is the set that you're going to align, and you're aligning it to, let's say, the second point cloud, which is Y. You compute the closest point in P for every point in Y. So that means if I have 30,000 points, typically a laser scanner will give me 30,000 points on the face. I will find the closest point in the second point cloud for 30,000 points. And then I will do the rotation translation, which minimizes my point-to-point error. And I'm going to do this iteratively until it converges somewhere. Okay? So the minimization basically is, so this is the target point, which is the closest point. This is a rotation matrix represented with this quaternion. This is the original point that you're transforming. And this is a translation. So rotation and translation. You can add here a scaling, but if your 3D scanner is a metric scanner, you don't need scaling. It gives you real metric information. So then you, as I said, you apply the registration. That means you do your rotation and translation. You obtain a new point cloud, and you do this again. Okay? So you terminate if the error is below a threshold, and then there are some values that you can set for a threshold that are indicative of shape size. Now the thin plate spline, as opposed to ICP, deforms the surface. And the way it is defined is it uses this special surface function, which is depicted here. R here is the distance to the origin. So I give you an XY coordinate, but you take the distance to the origin, which is here. Okay? It's like a dent in a thin plate, right? You know, if you have a thin metal plate and if you make a dent in it, that kind of looks like this. And this is the idea in thin plate splines. Like you have a metal plate where you're nailing it to some other shape, and the points where you nail it are exactly matched, but everything else is interpolated because the thin plate kind of bends according to the surface deformation. Here's an example. Suppose I give you a face, a neutral face, and this is also what I meant by idiosyncrasies. You see, the person looks like it looks like a smiling face to me, but it's his neutral expression. So there is some variation. This is his actual smiling expression. So what has happened here is, once we have good registration, we can find a deformation field from this image and then apply it to this image by identifying some landmarks, and then morph this image according to this deformation field. Now you get these ones because the teeth are not here. It's not visible in this image. So it's basically a one black pixel stretched over a larger area. So you can open a mouth, but you will never produce teeth by doing this kind of morphing. Now, the problem with ICP is, well, let me first tell you whether they're beneficial. The thin plate spline, if you have accurate landmark, is a better registration. Okay? However, it disturbs discriminative information. In the limit, if you use all the points in the face, you get exactly the same thing as the thing you're deforming. So all discriminative information will be hopelessly lost. So the trick in thin plate splines is to use a few points, but a few very accurate points. Okay? ICP, however, doesn't disturb your model, so all the discriminative information is there because it's rigid. It doesn't change it. It just rotates and translates. However, it's very expensive. In a recognition scenario, typically, if you have 1,000 people in your gallery, and if a new face comes, you need to check it against all the 1,000 faces, which is very expensive in ICP. So what people do is they create an average face model, and when a new face comes, they ICP it to the average face, establishing one-to-one correspondence with the pixels of the average face model, which is already in correspondence with existing faces. So suppose I'm trying to recognize 180 expressions. I have, let's say, a gallery of expressive faces. I create an average face model. I establish correspondence of this average face to all these expressive faces. And when a new face comes, I just establish its dense correspondence with ICP to the average face model, and that will automatically give me correspondence to all the existing models that I have. Now, this average face model is one of the bottlenecks here. You have to be very careful in selecting your average face model, because this is how you're going to do your registration, right? And this is how you're going to measure the deformations. You're measuring it with respect to the average face model. So if your average face model is bad, then the deformations you're getting will not be correct. So here is an example. Some years ago, my group in Amsterdam, Nico Sebe and Theo Hevers, received a lot of media attention because Nico applied his emotion model on the face of Mona Lisa. And he showed that the Mona Lisa is 83% happy, but 8.8% disgusted. And this somehow fascinated art historians and the art world. You know, they had a lot of media coverage. But what he did was he fitted this Bezier volumetric 3D mesh on the face of Mona Lisa. But how do you then compute the emotions? You need the neutral face of Mona Lisa in order to compare where the facial points moved, right? What Nico did was he took 10 Mediterranean women of roughly this age, and he constructed an average face with their faces. So he actually did a clever thing. He took similar faces and he used their neutral faces to create a reasonable average face model. Now, let this be a lesson to us all. When we're doing face analysis, it pays off to use different models for dimensions that are obviously relevant. For instance, male and female faces. Female faces are typically 30% smaller. So why don't we use female average faces for registering female faces and male averages for male faces? And also ethnicity, Caucasian, Asian, and African faces. Do you know the other race effect? Who knows here the other race effect? Okay. What happens when you look at sheep? Can you tell one sheep from the other? You probably can't. But the herder can do that. And this is what happens to humans. When I go to US, if I see a lot of black people, I'm not going to be able to tell them apart, because I am not exposed to black faces from childhood on. Okay? What happens is I haven't learned the discriminative dimensions of that sort of face morphology. And they will have the same trouble with white faces or Asian faces. If you have been exposed to the different races from birth on, you won't have this problem, okay? Now, let's say a Chinese kid raised in Istanbul will have no trouble separating Turkish faces from each other. He may have trouble separating Chinese faces if later on he goes to China, because he's not exposed to these dimensions. So this is called the other race effect. But it has a basis, okay? So morphology, ethnic morphology, is a discriminative dimension of the face space. So when we were working on 3D face analysis, we said, okay, let's create different average face models, and we have shown on the FRGC dataset that registration for males and females, for instance, was better this way, and also ethnicity was helpful. But then we said, okay, we're assuming that these morphological differences exist in the face space, right? That the African, Asian, and Caucasian faces are in fact different from each other. Why do we need to label them? Why not do a simple clustering in the face space? All right? So we did a 6 means clustering on the shapes on the faces. And look what we got. These are the 6 means. Here we have the gender decomposition for the mean, for the samples that fall under this mean, etc., and the ethnicity distribution. Now, the ethnicity is not the true ethnicity. We just label them according to what we perceived it to be. And in the database, we had very few African faces. But we did have Asian faces. And we had, look, the automatic clustering found 2 dominantly female clusters. And here, 1 dominantly Asian cluster. Okay, so actually, the ethnicity and gender kind of emerged as distinguishing dimensions. And that's actually this way, doing it this way is kind of more ethical. You don't need to put ethical labels, ethnical labels on people's faces. So the lesson is you should choose your models carefully when registering. Okay? And faces have different sorts of variations. And once okay, so for registration, I said ICP is quite useful, but ICP is a complex optimization problem. If you, just like active appearance models, that's also iterative. If you start either ICP or active appearance models from a poor initial point, you will converge to a local optimum and you will not get the good solution. This weakness of the appearance models and ICP is very well known. So usually, ICP is started with a coarse registration. Typically, what people do is you find the nose tip, and then you align the face with the nose tip, and then you continue. In 3D, the nose tip is somewhat easy to find. Here, you see samples from the FRGC dataset, and you see that some of them have really bad illumination conditions. So automatically landmarking this data set is actually a very tough problem. It's almost, so you were doing this facial landmarking to do face analysis like recognition or expression recognition, but the landmarking may be even more difficult than the thing that it's used for, right? Because now we're dealing with smaller things, smaller cues. And here, I mean, visibly, it's almost impossible to do ground truthing here. So how do we do this? The active appearance model basically jointly optimizes landmark locations, and the elastic bunch graph also does that. That means you have a very complicated optimization term that can be affected by a lot of things. If I have, for instance, sunglasses, then the information that should be coming from the eyes will simply not be there, right? The feature information is not there. So this will affect your global optimization. That's why we went for modeling the appearance of each landmark separately, okay? We constrain the search using the face shape. So you have detected a face, okay, you have a bounding box. Now there is a certain area where you expect the eye corners to be, right? Or the nose tip. So you can actually constrain your search. Then we also check the structural relations between landmarks. to correct wrong landmarks. If I detect the nose tip here and the mouth corner there, it's obviously wrong. It should be the other way around. So I should check the structural corrections, but in a way that is taking account the rotations in the faces. And then using a coarse to fine approach is really helpful, because when you're looking at faces in a coarse scale, if you, let's say, analyze a small window, then there is much more feature, much more uncorrelated pixels in the coarse scale. If I really zoom into your face, let's say, then all the pixels will have similar intensity values and they will be really correlated. So in the fine scale, the correlations will hinder your learning. You want, as you know, as much uncorrelated data as possible to do your learning. So what we typically do is we downscale the image, we find a coarse location for the landmark, then we go to a next scale, maybe in a pyramid scheme. We search around this point, and then we go to the even higher scale, and then search around this point. So we proceed from a coarse to fine. This helps both accuracy and speed. What we did was we used Gabor wavelet filters in 8 orientations and 3 scales for the landmarking problem. Gabor wavelets are really useful for emphasizing the facial information, as I said. We took 7 by 7 pixel patches around each landmark, so that means 49 features per Gabor channel. And then we trained a mixture model for each landmark, so the appearance was statistically modeled. Now I'm going to open a parenthesis here, and I'm going to present you an algorithm to do that. Because actually, Fernando had a slide on probabilistic PCA, which is a related model, but he skipped it very quickly. He didn't talk about it. It's in your booklets somewhere. But the statistical model we used was essential in the success of the algorithm, so you should know a little bit more about that. This is a general expression of a mixture model. What we do is we have a point set, and we model the point set as coming from a number of distributions. So here you have the probability of a component, and then probability of a point coming from a component. Right, so this is, for instance, a mixture with 3 Gaussian components. Each of them is represented by a mean value and the covariance. And the shape of the covariance matrix basically gives whether this is a sphere or an ellipsoid like this. Can you tell me, for instance, which of these components is the spherical covariance? This one. So a spherical covariance means that you have the same variance in each dimension. That means this covariance matrix can be expressed with a single parameter. It's this one. And this also tells you that the variance in this dimension is the same with this dimension, so what you're getting is a sphere. Here it's a circle, but in 3 dimensions it's a sphere, and in n dimensions it's a hypersphere. This is like the most parameter cheap way of expressing a Gaussian, a single parameter. You can do a little bit better by saying, okay, let me allow different variances in each dimension. And that will give you a diagonal covariance matrix with n parameters, n being the number of dimensions. This red one is, for instance, a diagonal covariance matrix. Okay? Here you have a large variance in the x direction, a small variance in the y direction. So it's like pressed. Now, a diagonal covariance allows you to press your data from any dimension, but it doesn't allow you to rotate your data. Okay? Because when you rotate, you get correlations in your dimensions. Here, for instance, if I tell you that I have a high x value, you will tell me that you will probably also have a high y value, because there is a positive correlation in x and y dimensions. So this is now a full covariance component. Okay? So it's 2 by 2 actually, and this is symmetric. So sigma 1, 2, sigma 2, 1, they're both positive. If I want to tilt it this way, then they become negative, because then I'm basically saying if I'm increasing x, I'm decreasing y, and vice versa. So why is this necessary? Why am I telling you all this? Because a mixture of Gaussians is the most flexible statistical model for modeling any kind of distribution. Actually, by increasing the number of components and by toying with their shapes, you can model arbitrary distributions. And it gives you the benefit of local models. If your data set is really complicated with a lot of different clusters, then you can put there a lot of components. But if it's just one big blob, then maybe a single simple Gaussian will be enough to model it. If you look at this log plot, the number of dimensions determines the number of parameters that you need to spend for the covariance. And a diagonal covariance, if you have 200 dimensions, a diagonal covariance will have around 200 dimensions, basically. But the full covariance scales quadratically. So as you move in this direction, the difference between a diagonal covariance model and a full covariance model will quickly grow. Okay, so here you have like 100 times more parameters than this one. And that becomes a huge problem, as Fernando also told us, because when you're training, okay, when you're doing statistical modeling, you need data points proportional to the number of parameters. So we want to keep the number of parameters very small. And he showed you a lot of models that do like PCA, okay, and one of them was the factor analysis model. In the factor analysis model, we assume that the data that is in, let's say, high dimensional space is actually generated in a low dimensional space. Let's say this is 3-dimensional, and I have generated it from a univariate distribution in 2 dimensions, and then I multiplied it with a factor loading matrix, which is, let's say, P times D. P is a small dimensionality, and D is the large dimensionality. And I transferred it to this high dimensional space. And then I carried it, maybe I translated it with this mean vector. And then there is some noise. So the factor analysis model basically, given this high dimensional space, tries to recover the factors. And as Fernando also said, it's kind of like PCA, but in a probabilistic way. Okay, the factors are actually distributions in the low dimensional space. There is a way of learning a mixture of factor analyzers for a given data set, which is very similar to mixtures of Gaussians, except that each Gaussian is expressed as a factor analysis model. I'll not go into expectation maximization, but the idea is the same with k-means. I think many people know here k-means, right? In k-means, what do? You first randomly assign means to data, and then you find which point belongs to which mean, and then you update the means, right? Well, k-means assumes a spherical covariance because you're using the Euclidean distance, so every dimension contributes equally. Replace this spherical covariance with a Mahalanobis distance, where covariance structure comes into the picture, you obtain a Gaussian mixture model. Okay? Very simple. And this is also the same idea, but in a soft fashion. So you don't count the number of points one by one. You just add their probabilistic contributions. What's the probability of coming from this mean? What's the probability from coming from this mean? And you add these. So the incremental mixtures of factor analyzers method that we use is a way of learning how many components there should be in the mixture. We start with a single component, single factor mixture, and then at each step we either add a new component, we split one component, or we add a factor to one of the existing components until a cross-validation criterion is satisfied. We select the component that looks least like a Gaussian by observing a multivariate kurtosis criterion, and we split that component. For instance, let's say I have this data set. This is the initial one factor, one component solution. We look at its principal direction and from the mean go either way, one standard deviation, and use these as the new seeds of the components. And then we split it. EM is continued, so it converges to another solution. Then in the second iteration, this component looks least like a Gaussian, so this will be selected for splitting along the PCA axis. And this will be the solution that the model finds at the end of the run. So it will try a fourth split. This one will be selected as it looks least Gaussian, but the split will not increase the likelihood in the validation set, so it will say, no, I'm not going to do this. 3 was enough. So this model adaptively tunes the model complexity according to the data complexity, right? And it kind of answers the question, how many clusters shall I use? Well, you don't need to answer this. You just run the algorithm. It will incrementally do this for you. I'll skip the factor addition, but here's, for instance, an example. This is the UIDA spiral data, and if I run the factor analysis model, it will basically fit mostly three-dimensional manifolds in a small neighborhood. So it will actually model this distribution piecewise. Okay? But this allows us to model all sorts of model of intermediate complexity between the diagonal and the full covariance model. Because the factor loading matrix is D times N instead of D times D or 1 times D. So depending on the number of factors, you can linearly explore this space. Okay, I can skip this one. So we're going to train these models on each Gabor channel and then basically use it to locate the facial features over the whole face. We use a probabilistic shape to constrain the landmark locations. It's basically a Gaussian conditioned on the face boundary. So if you have cropped your face like this, let's say the eye corners will be somewhere here. We learned this from the training set. But some landmarks are more stable than others. Like your eye corners, they don't move much. But the mouth corners, as you do your expressions, they move a lot. So they're unstable. So what you want to do is you want to first find your stable landmarks and then constrain the unstable landmarks using the stable landmarks. The second thing we do is, suppose you have detected the landmarks, but we didn't use an active appearance model. We tried to detect them individually, and we made some mistakes. Okay? So here, let's say the mouth corners, because of the mustache of this person, were located in some incorrect location. What we do is we use the structural relations between landmarks to guess which landmarks can be wrongly estimated. And the way we do is like this. Suppose I treat this as a shape. So 7 landmarks, XY coordinates. Remember the Procrustes analysis, which kind of created a consensus shape? Now, if you want to do shape analysis, you usually transform your shapes to a uniform space, where they're centered on the origin, they're scaled to have a certain, let's say, average distance to the origin, and then they're rotated so that one of the landmarks is at a known location. And then this makes all the shapes comparable. But while doing this affine transformation, if one of your landmarks is erroneous, you will make a mistake, because you're translating all the landmarks to the mean landmark. So the mean is translated to the origin. But if one of them is wrong, then the mean will be wrong, right? So the idea is this. Suppose we do this kind of normalization by looking at only 3 landmarks. Okay? I translate the mean of these 3 landmarks to the origin. I scale it so that the average distance is 1. And then I rotate so that the left eye is along the y-axis. And then I do this on the training set, and I look at the distribution of the remaining landmarks. And they can be adequately modeled as Gaussian distributions. Now, the idea in the Golomb algorithm is, when I do this, suppose this is my support set of 3 landmarks. These are the ellipsoids where I expect the other landmarks to be. If I have, so these are completely off the mark, I can tell. They're not in their expected ellipsoids. I can detect them as incorrect landmarks. But the idea here is, I have to do this for all triplets, all possible support sets, because I don't know which support set is reliable. But if my support set, if one of the landmarks in my support set is wrong, then all the landmarks are scattered to the winds, because the normalization is then completely wrong. So I can use the remaining landmarks to validate my support set. I can evaluate, there are only 35 support sets with 7 landmarks. I can look at all of them, they're very simple to compute, and then choose the best one. What does this give us? Well, suppose this was your facial landmarking. I gave you the points, but I didn't tell you which ones are wrong. You pass this through Golomb, this is the result you'll be getting. It will automatically say these 3 are the most reliable support set, and then decide that these 2 points are off the mark and re-estimate them through their expected locations. Or here, for instance. If this is the result of your automatic landmarking, again, you don't know which ones. Actually, Golomb doesn't use image information at all. I'm just telling Golomb the XY locations of these points. And it will tell me this is the correct location. Okay? So this is a way to cope with corrupted appearance information. If you try to run active appearance model on this image, it will not work. Because it's expecting a lot of features along the chin boundary. They won't be there. So the global optimization will completely fail, right? So this is, well, on the Bosphorus database, the success of this model on different landmarks, outer eye corners, inner eye corners, you can see here. The tip of the chin is pretty difficult because there is not a marked point on the tip of the chin. All the area resembles each other. But if you use further constraints, like the appearance model, for instance, does, then you can also correct for that. Why did we use this incremental model? Well, we could have used other things. We could have used the Gaussian mixture model. If you're familiar with the work of Figueiredo and Jane in 2002 to train Gaussian mixture models in a non-supervised manner, this is the algorithm. Or support vector machines trained on feature patches, or just taking PCA. So here you see the test database is Bosphorus or FRGC. The training is on Bosphorus. You see that the results of the incremental model is much better. And here the columns are, this is with region of interest, like just taking a square around the expected locations of the landmark. And this is the Gaussian prior that kind of constrains the expected location probabilistically. And this is, these are some results from the literature. Christinace and Kutz, 2006, is the blue one, the active appearance model. Here you see the acceptance threshold, and here you see the accuracy. So in landmarking, what we usually do is we say, okay, here's your ground truth, and here's the landmark that you have detected. Are you going to accept it as true or not? Well, I'm going to use a threshold. If the distance is less than 10% of the inter-eye distance, I'm going to say, okay, that much error is acceptable, I accept it. And so we usually plot our curves based on this acceptance threshold. And 0.1 is the basically state of the art. It corresponds to 6.2 millimeters, I think. So you should basically look at the accuracy at this level. But this curve gives you a more general idea, right? So this is, these results are from Maya Pantich's group at Imperial College, and Milbaron-Nichols is the STASM model, the extended active shape models. And this black one is the incremental factor analysis. We also like to report cross-database results, especially in face recognition and face expression research. There are a lot of databases. You have to be careful to produce as general results as possible. And one way of doing this is you train your model completely on one data set and then test it on a completely different data set. That shows that your method can generalize. You're not overlearning specific illumination conditions of the database or resolution conditions. So here we use Bosphorus, FRGC, Concanada neutral, Concanada expressive. And you see that when you do the training and testing on the same data set, you have high accuracy, but sometimes, usually actually, when you go to another database for testing, the accuracy drops. Sometimes some of these databases are more rich in terms of variations, so they can be even better in training than the test data set. So here you see the nose tip is localized better if on the Concanada. Concanada is simpler in this case, so there can be some little variations, but in general there is a big decrease in accuracy. So let's say we did find our landmarks. How are we going to do the expression recognition? Well, we use our landmarks to fit a model on the face. And we can use the thin plate spline. If you have accurate landmarks, it will work very well. Then we track this. Shall I? Okay. So we fit a model based on the landmarks that we have derived. And we do a tracking. Basically, we track these points over a video frame. And then we look at certain points, like the 12 points annotated on this mesh, and we look at their movements. So I have the neutral face, I have the expressive face. I look which point moved where, how much. So I just need to extract a 24-dimensional vector, the xy, or maybe even not that, just if I use the directional model, I just need one value per dimension. Okay, so these 12 points, how much did they move in those directions? And I use a naive Bayes classifier on these motion units. They're quite different than actual action units, but they give good results if you have a good landmarker and registration. So here are some results. The test set is the Concanada or the Binghamton 4D dataset. The landmark support is either by Viola-Jones, by the automatic system that I just described, trained on Bosphorus or FRGC, or by manually annotated ground truth. These are the 6 basic expressions, and this is the average accuracy. So let's look at the average. If you use the Viola-Jones to register your faces and do not use any landmarking, your accuracy is 70% on Concanada and 64% on the Binghamton. If you use the automatic landmarker, you get significant improvements in both datasets. If you use the manual ground truth, you'll get even better naturally, right? So, because the landmarking also makes a certain degree of error. So, obviously then, registration and landmarking is crucial for expression recognition. For a good landmarking algorithm, you want minimum dependence on heuristics. You want to be detecting as many landmarks as you want, and you can't devise a heuristic for each landmark. You want robustness against pose, illumination, scale, expression, occlusion, etc. Everything that plagues face recognition, basically. If they're amenable to dynamic tracking, that's a bonus. For instance, active appearance models are nice because you can build a tracker with them very quickly. Of course, you want high accuracy and computational feasibility. You shouldn't be computing them for over a week. It should be real time if possible. And it should be applicable to data collected under different conditions. Any questions about registration and landmarking? Because they're interconnected somehow. So I gave you kind of like an intermeshed presentation of landmarking registration. Okay. Now, registration and landmarkings are actually problems that exist in other type of domains. You know, if you're dealing with audio, dynamic time warping is basically just the registration of two audio signals, and you may also need landmarks there if you have, let's say, word boundaries that can act as landmarks. So the concepts are somewhat more general, but this is especially important for face processing. I come to the final part of the talk, which is classifying facial effect. The first thing that we do for classifying facial effect is to choose a good representation. This is the mesh model that is typically used in active appearance models. This is the Bézier volumetric curve, the wireframe model used in Cohen and his colleagues, that we also used in Amsterdam. The complexity of this mesh or complexity of this model will affect your processing. You want sufficient expressivity here. And a very typical pipeline, let's say for classifying action units, is the pattern recognition pipeline that you're very familiar with. You find your features, you do your registration, you extract some features. Gabor wavelets are very typical. You do a feature selection with AdaBoost. You feed them into an SVM per action unit, and you do your classification. Okay? So this is from the UCSD group, Marion Bartlett. They have created this expression toolbox that Fernando also showed in one of his slides. It's called CERT. This is the basic processing pipeline of CERT. Now, we have known for a time that the temporal information is also important. So here you see the temporal unfolding of a single action unit for smiles. It's very relevant for smiles, unit 12. And different facial features show different profiles in time when this action unit is happening. And what people usually do is they separate this temporal profile into three phases: the onset of the expression, the apex, and the offset. I told you that Ekman thinks that just looking at the apex is a good summary of the expression. So when you're looking at the literature, for instance, on the COM-Canada expression dataset, most results are reported for the frames where the expression is in its peak. And the dataset is cropped so that the last frame is the most expressive frame. So it's enough for you to compare the first frame, which is neutral, with the last frame, which is kind of simplified, right? Because in a natural setting, you don't have segmentation. Segmentation is a different problem. So you have to find a neutral phase, and then you have to continuously evaluate what's going on with the expressions. There was a very old study in '79. What Basile did was he recorded 6 actors doing expressions in a video. He had several conditions. In one of the conditions, the actors' faces were completely painted black, but 50 points were marked with white markers on the faces. And people, when they saw a static or a 3-second dynamic display of a facial expression, then had to give judgments which expression that was. And what he found was, with the moving faces, 60% correct. With the static faces, only 30% was correct. So dynamic information, for humans at least, is very informative in classifying expressions. And these are just the basic expressions. For subtle expressions, the matter may be even more important. So tracking is one of your tools that you use if you're doing the temporal analysis. Okay. Accurate landmarking registration, usually costly, so you do it on the first frame if you have a first frame. Otherwise, you have to do it every time you lose your tracking. And then you track your facial points, which will give you a smoothed trajectory, and then you can apply some temporal methods, like you can use HMMs, you can use recurrent neural networks, you can use newer variants of recurrent neural networks, like long short-term memory neural networks. And for tracking, you can use different algorithms. I won't go into these details, but we use the Bézier volumetric curve. Maya Pantich's group is using the Patras-Pantich particle filter tracker. Birbanu and his students recently introduced a SIFT flow, which is also used for tracking the whole face. So you can use any tracker and then get the expression information. When you have a video, and when you're going to train your models with the video, then which frames are you going to select to serve as prototypes of your expression? So Zhu and his colleagues, including Fernando de la Torre and Jeffrey Cohn, they looked at the temporal unfolding of an expression in their training set, and they selected very expressive frames as positive samples. They discarded the neutral-looking frames, and then they took distant frames as the negative examples. So what they did was they used the temporal dynamics to optimize their training set and improved the expression recognition accuracy. Another important discussion in the expression recognition community is, how do we do this labeling? We want to go a little bit beyond these basic expressions. Well, we can use the valence arousal circumplex space that I've shown you, and instead annotate each emotion with continuous variables in these dimensions. Now it gets a bit more tricky to obtain consensus of interrators, but then you have a regression problem instead of a classification problem, which can easily be converted into classification, But it can be helpful in, a more granular, fine analysis of facial expressions. So I'm going to give you a few more examples, and then I'm going to conclude. Here's an example, again from the UCSD group, in detecting pain. Apparently, the real pain and faked pain activate different facial units, action units. And how do we know this? Well, we don't know this. The psychologists know this. So we work with psychologists in understanding what is the manifestation of a certain expression. If we have really good ground truth, we can also go the way that Fernando was promoting. We can do an unsupervised clustering and see what kind of emotions have been exhibited. Like, I have, let's say, a lot of sadness videos. I do an unsupervised clustering and try to see what kinds of sadness there are. That's also possible. But this is important for applications where your patient is unable to tell you how much pain he or she is feeling, and then you want to do this automatically. For instance, there is there is something in his mouth, or under some sedation, etc. Here's a recent database, UNBC McMaster Shoulder Pain Expression Archive database, where they have recorded people under pain, under real pain, which is kind of difficult, right? You can't give people pain artificially to collect data. So you have to find a place where pain is occurring naturally and obtain the permission forms from people in pain, which may be really difficult, and then record this in controlled conditions so that it's a useful database. Here you have the processing pipeline, again, video in, tracking with active appearance models. The feature locations are selected, an SVM classification, and regression-based, logistic regression-based fusion. The same UCSD group now detecting drowsiness. Have you ever driven a car in US? No? Well, they have these very large lanes going straight for miles and miles and miles. And they're very heavy on people who are violating speed limits. So you go with 70 miles, straight for 3 hours. It's very boring. And nobody, the same cars will be there 3 hours later. I mean, I learned how to drive in Istanbul, which is even worse than Napoli. So for me, it was really very difficult to drive in US. But so they found a solution. They're implementing smart cars that can detect the drowsiness of a driver. And then, it can switch to Rammstein for a while to wake you up, and then you can continue with Tchaikovsky. But what it does is, you see, head motion is observed, because you probably, when you're drowsy, your head is just doing these abrupt motions. And the eyebrow raises and eye openness. Okay? So facial expression recognition can be useful for smart cars. Another application is 3D modeling. If you can detect my facial expressions, you can translate it into my avatar, which is in Second Life, let's say, or in World of Warcraft. So in the gaming sector, this kind of analysis, then synthesis, has a lot of applications. We're not limited to 2D and 3D modalities. Theo Pavlidis was looking at thermal cameras for stress detection. So the veins around the nose area apparently can indicate whether you're under a lot of stress or not if you look at with the thermal camera. But it's a very expensive modality, so I think FBI has a few, but nobody else is using this. This is an application that is similar to what Fernando showed you. What he did was he took a footage of babies' videos and then he created a summary. We wanted to do something else. Have you ever watched the Harry Potter movies? Yeah? So did you remember the photo frames in Harry Potter movies? They're magical, right? The people in those photo frames actually wave back at you, so they follow you. They can maybe even talk to you. So that's what we wanted to do. We wanted to implement a photo frame which kind of interacts with its user. And the way we do it is like this. So I take a lot of videos from my baby, and this application is commissioned by my mother, actually, to be perfectly frank. So the system automatically analyzes these videos and finds segments. And what we do is we look at the optical flow and calm locations, like where the optical flow is at its bottom. Actually, we use this for marking the boundaries of the frames. So we create a segment library, little segments. Then we analyze the expression on the baby's face in those segments. And when the video frame is operating, it actually looks at me through a camera and tries to match my facial expression and my activity levels. So this will be the first frame that is existing in the video. This will be played in the loop. It actually played once at the moment, but it's very static. So he's sleeping here. So the photo frame will show a sleeping baby, basically, when it's not in use. And when a face is detected in front of the frame, the baby will wake up, basically. So you'll move on to the wake-up sequence. And then, depending on the valence and arousal of the person in front of the photo frame, different segments of the baby, of the video, will be activated. Another application that we did with this is distinguishing spontaneous smiles from posed smiles. Now, you can use this, for instance, to train actors to appear more spontaneous, for instance. Guillaume Duchenne in the mid-19th century predicted that there is this distinction between spontaneous and posed smiles. And Ekman has confirmed this later on. And what they call the Duchenne marker is basically what it distinguishes these smiles. So, can we see anything here? Is it running? So this is one smile. Here's another one. Can you tell which one is a posed or which one is real? Which one is real? The left or the right? The left. Yeah, this is not a very difficult sample. So this was a real smile and this was a faked smile. What gave it away? How did you know that this was not a real smile? The eyes. Okay. The eyes are very revealing. That's true. And that's where the Duchenne marker is actually. So you have two involuntary muscles, the orbicularis oculi and the zygomatic major. And the orbicularis oculi, so the zygomatic major is the lip, it pulls the lips upward. And the orbicularis oculi forms this little crow's feet kind of wrinkles around the eyes. There is recently also convincing evidence that this Duchenne marker, this crow's feet, is consistently used by untrained people to recognize spontaneous and enjoyment smiles, the post smiles, but it's not 100% reliable. People can do post smiles with this muscle, or people can smile genuinely without this muscle. But I take it that really professional actors, like Anthony Hopkins, for instance, probably can control all the individual muscles in his face, because this is how he appears to be really realistic, and that's why we say he's a very good actor. He was really believable, because you know it or not, you can tell this. Until I ask you what gave it away, maybe you haven't never thought about what gives it away, but as a gut feeling, you know whether an emotional expression is a spontaneous expression or a posed expression. But people do use both for social purposes, and we accept both. So if it's your birthday, I will smile. I'm not happy that it's your birthday, but it's a social cue. It shows that I'm being friendly to you, and you accept it as such. Okay? You don't think that I'm really happy, genuinely, felicitous, but you accept my my attempt of showing you that I'm happy for you. So we did an automatic analysis system for that. We used the same landmark localization and tracking algorithm, but then we looked at the eye corners and eyelids in detail. We didn't look at the appearance of the Duchenne marker. We looked at the dynamics of of the eyelid. And what we managed to show with a hidden Markov model-based classification is that just by looking at the eyelids and eye corners, you can classify this spontaneous versus post smile with 80% accuracy, which was done in a very small database of 20 subjects. This is a BBC. And here you see the same videos. Let me see whether I can make it work. No, in Mac, this bar actually is right over the, well, yeah. Anyway, if you just look at the smiles, let me run it here again. Just look at the eye region. Okay? Just look at the eyes of this girl. There's no smile in the eyes, so it's kind of obvious when you look at it that way. In a more recent study, we looked at more dynamic features for this problem, like the duration, amplitude, acceleration, etc. So all kinds of dynamic features. And our experimental setup was, again, we used the landmark-based registration and Bézier volumetric tracking. We normalized the track points with respect to the head pose. We trained SVM classifiers on different facial regions. Did a feature selection, and then we analyzed these dynamic features for onset, apex, and offset phases. So we did processing for different phases in a separate way. But as I said, this BBC data set was really too small. We collected a very large data set. This was collected in the Science Museum Nemo in Amsterdam. Anybody has been ever there? It's a very nice place. If you ever come to Amsterdam, visit it. I'll recommend it to you. They also have a very nice program that's called Science Live, where scientists are invited to, there's a special room for that in the museum, and you can set up your experiment there, and you can record data for 3 or 5 weeks at the very busy period, you know, when the schools are out. So you will see a lot of people coming in, and they have the chance to take part in a scientific experiment, which is really nice, but which also gave us a most amazing face database with an age range from 8 to 77. So we had the kids, the parents, and the grandparents. And our setup was so that people posed for expressions, but we also let them watch funny movies, and we recorded their spontaneous smiles and laughter. And the gender distribution is also balanced, which is quite rare in databases collected in computer science departments. So which region is more informative? The feature selection is the one that is before the SVM. The eyelid features, apparently, are the most informative, followed by the cheek and the lip corners. Here you see the temporal segments, the onset, apex, and offset for each of these regions. And it looks like that the onset of an expression is quite informative, because we're looking at dynamic features. I mean, if we were looking at static features, probably the apex would have been the most important part. And here is the result of combining information. Okay, you can have, because we're getting a lot of different results from different locations on the face, well, you can do an early fusion, mid-level fusion, just after the feature selection has happened, or decision level fusion. And apparently the mid-level fusion is better. And voting, well, it gives us quite 89% accuracy over a 400 subject data set. That's pretty good. Here are some other examples from the literature. Can you tell me which of these smiles are frustration smiles and which of them are happy smiles? Because Rosalind Picard and Hoek, they found that people also smile when they're frustrated. But people are very bad in finding this out. So who says that this one is a frustration smile? What about this one? What about this one? No? This one? Okay. Well, people are very bad. I mean, they perform less, almost at the chance level. This one is a frustration smile. This one, and this one. Or the other way around. I'm not sure. I'm also very bad. The computer is also very bad. The computer cannot tell this apart. But it's a difficult problem. They haven't found out a good solution to it. Okay, so David Matsumoto does a nice thing. He goes to the finals of the Olympic Games. This is the judo final. And he records the expressions. That's where real happiness, real contempt, real disappointment occurs. Can you tell me which one is the gold medal winner? The second one? Can you tell it by the facial expression, or can you see the medal here? From the facial expression. Okay. What about here? Well, here is the one who's holding the gold medal. Okay. Yeah, but Matsumoto also did this with beauty contests. In the US, you see these beauty contests on television where these girls act very unnatural, you know. The winner is announced, and there is this runner-up, and she is, of course, really disappointed. But then she smiles and hugs the winner and says, you know, it's awesome for you, I'm so happy for you. But Matsumoto captured the moment right after the winner is announced. And there is this expression of pure hatred. And then she covers her face and emerges smiling. So ecological validity can give you really interesting data, you have to admit. some of these emotional expression analysis tools are developed for social analysis. We have some collaboration with a clinical psychologist, Corinne Dyke, who's looking at facial mimicry. When people talk to each other, they mimic each other's expression involuntarily. That's a way of showing rapport. Okay, so I agree with you. I'm with you there. I listen to you. That I can see in the mimicry. Another application by Rana Al-Kaloubi in MIT, she started her own company called Affectiva. She was working on emotion readers for autistic people, because autistic people cannot read facial expressions, usually. They need external help in doing that. Ekman himself is doing a lot of clinical and psychological applications, trying to diagnose depression, schizophrenia, psychosomatic disorders, suicidal tendencies, guilt. One of the most difficult ones to understand is shame, for instance. Can you tell whether somebody is blushing? Very difficult, because gathering data is almost impossible, because blushing cannot be induced. Well, it's an involuntary emotional expression. It would be very difficult to collect data for that. There is also applications for impact assessment for marketing, the type of scenarios that you've been looking at. And there are some grand challenges in the community. The facial expression recognition challenge. This was at FG in 2011. You can have a look at this link. It uses the Geneva Emotional Portrayal Corpus, about 1,200 emotional portrayals from different actors. And they ask you to detect action units or classify emotions in a discrete way. So the best per frame action unit detection rate is 0.62 as F1 measure, and the discrete classification rate is 0.84. And this is the baseline system. You see, here's my advantage. Eye detection is provided, registration with only the eyes, which is not a very good idea. Then there is a LBP descriptors are extracted from each of these locations. A histogram is built, and then you have a classification. You know, PCA plus specific SVM classifiers again. So you see SVMs and LBPs, and these are all very frequently used. Another challenge was the audiovisual emotion challenge, also in 2001. And that uses the Semaine corpus. Semaine and Humane were the two major networks of excellences working in the emotion field. The visual part of the challenge had 1.3 million video frames where faces and eyes are detected. So it's a huge database. 50 frames per second, and each frame is labeled with activity, expectation, power, and valence. 2 to 8 raters provided annotations, and again the baseline is block LBP with RBF kernel SVM classifiers. So you see that the creation of a challenge dataset is a monstrous task. You know, 2 to 8 raters annotating 1.3 million video frames. The UFA-NEMO database that I talked about is collected with 2D and 3D modalities. It's good for age estimation because it has such a huge age range. Facial expression. We also have head pose estimation. For each subject we have neutral poses, neutral speaking, which is also kind of lacking from the emotional expression recognition literature. You know, when you have the surprise expression, in the database you will see this. But what if I'm not surprised, but just talking and saying, oh, you know? So these things happen also during normal speech. A proper protocol should put normal speech frames into the database, and then your surprise recognizer should not label them as surprise, right? Because otherwise maybe you're just detecting oh, and that's not surprise at all. So you should be careful what you're detecting. That's the bad thing about discriminative classifiers. If you have a few classes and no garbage class, let's say, then your results may be really strongly positively biased. this is our setup. So we did collect with Kinect and with a high, this is the Kinect and this is the CMOS cam, high resolution. We had the color chart next to our recordings. And this is the room of the Science Live experiment, all decorated as if it's a scientist in the old times with a globe that doubles as a liquor store, which is kind of possibly the only, only in Netherlands you can find something in a science museum. This is the age distribution. I've shown you that. So these are some samples. So here you see the color chart, the time, and then this is the Kinect. Now, at that time, the Kinect Face SDK was not out. Now it is out, so maybe this is a bit too small for face processing. From 3D to 4D, I don't have much to say on 4D because there are only a few 4D databases around still. 4D means when you have 3D with time. There is a few scanners that are really very expensive that can acquire 3D information 25 frames per second. So you'll get 3D in time. And then you can do temporal processing in time. This is Ioannis Kakadiaris' group in Houston. It's a very recent paper. This is the pipeline for 3D facial expression recognition, a procrustes analysis, then an ICP, the iterative closest point, and structural analysis. Then for close fitting, they have a thin plate spline warping, but they don't warp the face to an average face. They warp an annotated face to the test face and then just discard it just to retain the labels. And then they have SVM classification. For 4D, basically, once they match the meshes, they track the mesh. So they consecutively fit. Because this ICP requires good initialization, one frame can serve as a very good initialization for the next frame. This is the Kinect face tracking. I haven't seen this in operation. I don't know whether you have seen it already, but it's out, the SDK for the face tracking. And it looks pretty well. I mean, this information would be nowhere near analysis, amenable to analysis with, let's say, point-by-point based models. This is too noisy. But apparently, in this case, joint optimization of landmarks makes sense. So the only question is whether this generalizes to different models, right? I mean, I can very well understand if you acquire, a short footage, let's say 10 minutes footage of my face, and then prepare an active appearance model for me personally, it would work very well. But a generic face for all of us may be more tricky. But we'll see. I mean, if you're a gamer, you wouldn't mind 10 minutes of, expressions in front of a acquisition program. So it may be a possibility. So, future directions, and this is my last slide. There is a shift towards natural and spontaneous expressions, and people are really trying hard to acquire data sets they travel to Olympics, not just because of that. Matsumoto is himself a judo fan, but detection of subtle cues, very difficult. Separating a sarcastic smile from a normal smile is at the moment beyond our abilities. There is more and more focus on temporal information and continuous and dimensional labeling, so beyond the basic 6 expressions. Multimodal approaches, fusing it with audio, fusing it with body language, fusing it with context information, especially in social signal processing. 4D approaches, they're coming, especially with Kinect. I'm sure there will be an explosion in Kinect-based facial expression analysis, and more data collection. That concludes my talk. Any questions I can take? Thank you.
Do you know of any database on micro-expressions? That's very quick expressions, that concept of micro-expressions?
Yes. So, well, spontaneous expressions can be classified as micro expressions, because, well, you mean the annotations, right? Yeah, I mean the concatenate is annotated for action units. That will give you the micro expressions. Yes, the CK plus will be suitable for that.
There should be a very fast expression, almost imperceptible.
Yeah. Yeah, so the temporal scale is a problem there. But some of the recent databases are acquired with very high temporal, well, 50 frames per second, for instance, and with very high resolution also. So the information is there, but the annotation is unreliable also because the annotators, they have to be, it's a tiring job. So one problem of face recognition research is, yes, our benchmark is the human, but the human is not infallible. We use Cohen's kappa or Fleiss kappa to look at inter-rater agreement, but Ellis O'Toole, for instance, looked at the performance of face processing in guards in the airport, and they become tired. They can't recognize the terrorists in their list. It's very difficult. So, yes, we can recognize people, for instance, or we can understand expressions sometimes very well, but when it's across cultures, we fail, as the recent studies show. So maybe the projected benchmark for our own purposes is just too high. The humans cannot actually do that. All right. So I have the Bosphorus database. So if you need it, just contact me. Okay.
Thank you.
Thanks.